That's when the game starts getting interesting.
Because you can get like rules and estimates.
Yeah, and then so
it gets more and more.
So our mathematicians then collaborate with our computer scientists to build simulations of this kind of game and the players, and we have some AI algorithms that will try to learn the defender's strategy to try to be like an optimal attacker. So if we just choose like a fixed rule for the defender, and it just chooses some number of times it's going to do this, say it just always lies. How long does it take the attacker to learn that? Right? So the other one is, have you ever heard of the Monty Hall problem?
Yes, I have.
You have? That's cool. No way.
I've heard of it. I watched Vsauce, so I...
Oh my gosh, I like that guy a lot. He's awesome. Yeah. No, he's got some great stuff. He has a great description of that problem.
It would be better to switch because the probability is different.
Right, but why?
To the left, it will...
Oh, it would be a curved path on its own.
It could go into your thing, or it could go and loop around to your own goal.
Yeah. It's -2.
Minus 2, so they get 2 years.
That's
so
right.
So probably -1 here.
No, it's 1. No, it is -1. You're right. Yeah.
Because
that's the spot at which the game, neither player has an incentive to move or change. If you're here, you don't want to go this way. If you're player 2, you don't want to go this way. If you're player 1, right? And so you get stuck here in the Nash equilibrium. And so that's one of the types of equilibrium that we study for games like this. Yep, that's the Nash. Yep, we get stuck at the Nash.
I don't know.
You can't move out of that. Now, this game can also be played in multiple rounds, and that's when things get really interesting. Of being a car, okay. If we take those together, it's the sum of the probabilities, right? 1 and 3, 1 and 3 is 2 and 3.
And that has 0. No.
That's right. Now this is 0, right? Which is, not a 1 in 3 chance. So what that does is it says, we know this is fixed at 1 and 3, so this probability moves over here. Now this is 2 and 3. Because there's only 1 remaining, I know this probability is...
Almost I'm going to the right, it could just like stop and go back and stuff.
You could do that too. It could actually happen.
Oh.
You can hit it softly and it'll go...
Well, I watched Vsauce during class a couple times.
Don't do that. That's a terrible idea.
Well, I don't have
Unless your teacher is showing you unless you can talk your teacher into showing it. Which might not be a bad idea. To say, Vsauce has a great description of the Monty Hall problem. Choice because you'd think that would be the right way to do it. But if he knew that you knew that he was diabolical. I'm gonna take a half of this, just multiply by 1/2, right?
Because you have a decimal in a fraction. Two things that are normally conversions of each other.
The other way of figuring this out, right, is to say this one is a probability of 1/4, right? And we know we have 2 probabilities, so we have a probability of, say, we have P1 plus P2 equals 1, right? And we know P1 equals P2, probability of this door, probability of, say, P1, P2, right? So it's 1/4 plus 2P1 equals 1, and then we can do, we move the 1/4 over there, right?
Yeah.
And then we divide by 2. It's the same thing, right? But you can work it out algebraically too.
Just simple math.
It is, yeah. No, that's the cool thing about a lot of the game theory stuff. And this is technically not a game theory problem. This is more of a logical fallacy. It's sort of an exploration of probably reason for a game like this, and then we'll turn it into a piece of software, and then we'll have it run thousands of times with different strategies and see. Then we'll draw charts and graphs from the results, and then we write a paper and publish it.
That was one question with my phrases. Thank you. Thanks for not making me lose credit in math class.
Almost identical. They're prisoners, or they're going to be.